Hello everyone. So today we're going to be talking about the quotient rule. So in the last video we talked about the product rule, which allows you to take derivatives of the product of two different functions. And today we're going to be talking about the quotient rule, which allows you to take the derivative of the quotient, so division of two different functions. And this is actually, so I just spent, however long it was, 30, 40 minutes recording this video of this lecture, but then it turned out that I never pressed record. So this is my second try of recording this video. It's just one of the fun things about being an online teacher, I guess. But yeah, so before I get into the lecture, I just wanted to take an opportunity to remind you of a few things. So one is that we have a midterm coming up on Friday. So it's going to be very similar to how the quizzes work in terms of it'll be posted in the morning, it'll be due by midnight. Same kind of rules about what you are not allowed to access during the exam. So I'll be sending out an email with some more information a little bit closer to the test. The last material that you're going to be held responsible for on the exam will be stuff from yesterday. So quotient rule will not be on the exam. I posted a review, so you can find that if you go to the week 4 module, you'll see a file that says midterm 1 review, and that includes the solutions at the end, or the answers. It's like an answer key. And then I will also post on Canvas, I don't have it posted just yet, but I'll post a survey where you can tell me which questions you would like me to go over from the review. And then I'll be making a video most likely on Wednesday night and posting on Thursday where I'll go over some questions from the review. So it would really be helpful if you could just post or just fill out this survey so I know which questions people want me to go over on the test. So I think that's it for announcements. So let's get into my second attempt at this lecture. Okay, so last time we saw the product rule. Is for taking the derivative of a product. So a product means multiplication, right? So where to use the product rule? You would use it in a situation like what we did last time as our first example, which was x squared times e to the x. So two different functions that don't really blend together. You can't combine them or simplify in any way. So you would have to take the derivative using the product rule. So what was the product rule? Actually, sorry, I'll hold off. I'll write out the product rule. I'm going to write the product rule down again right before I write the quotient rule because it's very similar and I think it's nice to see them side by side. So today, what we're going to be looking at is the quotient rule. And the quotient rule is for taking the derivative of a quotient. So quotient means division of two functions. So an example of that would be if instead of doing x squared times e to the x, if you had a function that was x squared divided by e to the x. So just like what we did last time, I want to start by telling you how the quotient rule does not work, because even more than the product rule, I find that people really like to do this wrong. So what is not true, it is never, ever, ever true that you can take the derivative of two things being divided like this. You are never, ever, ever going to take the derivative of the numerator and divide it by the derivative of the denominator. It just doesn't work. That's just not the derivative. I'm sorry, I know it would be nice if that's how it worked, but it does not work that way. So in general, if you're trying to take the derivative of two functions being divided, that is not ever going to be equal to the derivative of the numerator divided by the derivative of the denominator. Doesn't work that way. So let's, like we did with the last one, I'm going to show you an example to hopefully convince you that it doesn't work that way. So how do we know that it doesn't work that way? So let's try an example. So let's say we have the function f of x is equal to x to the fifth over x to the fourth. So that is the same thing as just x, right? Like x to the fifth over x to the fourth, that's x. So we already know how to take the derivative of that. So the correct way to take the derivative of x would be f prime of x is equal to 1. So let's say that instead you tried to use this fake idea of taking the derivative of the numerator and the denominator individually. So what would you get? You would get 5x to the fourth on the top, and you would get 4x cubed on the bottom, and that simplifies to 5 over 4 times x, which is not the same as what we got over here, right? Over here we got 1, and over here we got 5 over 4 times x, which is completely different. So that tells us that this method does not make sense. It does not work. Don't do it. Okay, so now let's talk about what you actually do as the quotient rule. And before that, like I said, I want to write down the product rule again because they do have a lot of similarities, and I think seeing them side by side kind of might help you remember how the quotient rule goes. So the product rule, remember, tells us that if we want to take the derivative of one function times another function, how can we do that? We can do it by taking the derivative of the first function, so f prime of x, and then multiplying it with the second function, g of x, and then adding to that the derivative of the second function times the first function. And then that's it, sorry. That's the product rule. So what's the quotient rule? So the quotient rule is for when you're taking the derivative of now two functions being divided. So something like f of x over g of x. Okay, so how would this work? Well, first of all, the biggest difference is your answer is actually going to be a fraction. And so the numerator of the fraction is going to look almost identical to the product rule. The only difference is that you're going to be now subtracting instead of adding. So this, instead of plus, we have a minus. And then in the denominator, we're going to take our function that is originally in the denominator, so g of x, and we're going to take that function and we're just going to square it. We're not going to take the derivative or anything. We're just going to take that function and square it. So one thing I just want to point out that's really important is that in the product rule, because you're adding, it doesn't matter what order you do, right? You could take, like if you wanted to, you could switch the order of these two things. You could do g prime of x times f of x plus f prime of x times g of x, and you would get the same answer either way. With the quotient rule, it does matter because you're subtracting. So if you do this in the wrong order, if you actually flip these two, you're going to get, your sign will be off. You'll basically flip to the negative of what you should have as an answer. So the way that I personally like to remember it is I just always remember that you take the derivative of the numerator first. I feel like if I can remember that, then I can remember the rest of it because I know I'm taking the derivative of the numerator first. I know that like everything else kind of looks like the product rule except for we're subtracting, and then you're dividing by your bottom function squared. Okay, so let's do an example of using the quotient rule. So let's actually do the example from earlier. So if our function is So I think it was what? X squared over e to the x. So let's call our top function is our f of x, right? And our bottom function is our g of x. So what the quotient rule tells us is that we're going to start by taking the derivative of the first function, so f of x, so that's going to be 2x. And we're then going to multiply that with the bottom function, which is e to the x. And then from that, we're going to subtract, taking the derivative of the bottom function. So the bottom function in this case is e to the x, and derivative of e to the x is just e to the x. And we're then going to multiply that with the numerator, so x squared. So that part again looks just like the product rule except for with subtraction. And then we're going to take that and we're going to divide it by the bottom function, so e to the x squared. So one thing that is going to come up with the quotient rule is simplifying. So if you were to just write that as your answer, I would not give you full credit because there are some like pretty straightforward simplifications that can be done. So later on, I'll bring this up when we look at some other examples, but like there are some functions where, you know, there's multiple ways to write it and either way is fine, but there are certain things that I expect you to do. So one of the things that I expect you to do is if there's a common factor in the numerator and the denominator, I would expect you to cancel that common factor out. And so in this case, we have a common factor of e to the x in the numerator and the denominator, right? So I'm going to factor out an e to the x in the numerator. And so we're left with 2x minus x squared. And then in the denominator, well, e to the x squared is the same thing as e to the x times e to the x. And so now we can see that we have a common factor of e to the x. And so we're left with 2x minus x squared over e to the x. And that would be our final answer. And a lot of students like to ask me about factoring. So like, for example, if you were to write your answer instead like this, if you factored out an x from the numerator, that's fine. I mean, there's nothing wrong with doing that, but you don't have to do that. So why do you factor in general? It's usually when you're trying to solve something. So for example, if I had asked you, like let's say in this question, if I asked you, where does this function have a horizontal tangent line? Well, then you would want to take the derivative and set it equal to 0, right? And if you're setting something equal to 0, well then yeah, then you want to factor. But if you're just kind of giving me your answer, there's really no reason that you should have to factor it. So really, I would say only factor if you're solving something or if you're trying to simplify. So if you're trying to simplify like we did in this problem, you know, factoring out that e to the x helped us see that we could simplify. But you know, this kind of factoring that we're doing over here is purely optional. Okay, so we're not going to do a proof of this. So I just want to do like a handful of more examples. So we're going to do like 4 more examples and getting kind of progressively a little bit more complicated, and also kind of point out some situations where you do and do not need to use the quotient rule. So here we're just going to do some examples. So one thing I just want to quickly mention, and maybe kind of going back to something I just said on the previous page. So I just mentioned something about, oh, like say you wanted to find where this has a horizontal tangent line. So all of these derivatives, you know, we're learning new derivative rules now, but the same like concepts of derivatives apply. So every function has only one derivative, right? You can find that derivative using the limit definition, but we're not really doing that anymore. Now we're focusing on using these derivative rules because for the most part, they're a lot easier. So we're using these derivative rules, but everything that we say about the derivative is still the same as what we said like last week and the week before. So the derivative still always tells you the rate of change at a particular x value. You can still use the derivative to write the equation of a tangent line. You can still use the derivative to figure out where does the graph have a horizontal tangent line. You can use the derivative to figure out whether the function's increasing or decreasing. All that stuff that we've been doing, we're going to kind of keep doing that just like peppered throughout the course. So every time we learn a new derivative rule, you can still do all that same stuff using these new derivatives. That being said, I'm not always going to do an example of all of that stuff in these videos. So I would really, really recommend that you look at the worksheets, because sometimes the worksheets are going to be just kind of very similar examples to what's in the video, but a lot of the time I'm going to try to throw in a few other examples that are a little different from what we did in the video. And for me, like, if you take a class with me in person, my classes are not just me lecturing the whole time. It's kind of a mix of lecture and then doing worksheets in class. And so to kind of model that, I consider you doing the worksheet at home as kind of part of class. So, if you're like on the homework and you're like, I don't feel like Anna ever did an example like this in class, go look at the worksheets, because I write out the solutions in full detail on those as well. So those are kind of another resource, another place for you to get practice examples of questions. And I make the worksheets up myself. I pick the questions for good reasons. I pick them to kind of try to show you a particular type of example, or because I think it might help you on the homework or something like that. So like for example, on today's worksheet, there will be some examples that maybe have to do with finding the equation of a tangent line, or figuring out where a graph has a horizontal tangent line, things like that, that are basically applications of these new derivative rules. All right, so examples. So let's start out with a fairly simple example. So let's say we have the function x minus 1 over x plus 1. So I think this is kind of a deceptively simple example, because it almost looks like you should be able to simplify it, right? Like x minus 1, x plus 1, they look so similar, but there's actually really no way to simplify this. We'll see in a few minutes another example that you can simplify before taking the derivative, but this one you can't. And so here you really do have to use the quotient rule. So I'm going to show you a way that I personally really like to write down stuff when I'm doing the quotient rule, and I think this will be especially useful because next week we're going to start getting into some other derivative rules that kind of work in combination with the product and quotient rule. And one of the things that students have the most difficulty with is kind of keeping track of like the kind of order that you have to do things. And personally, I think that writing things out the way that I'm about to on this one really helps you kind of keep things in order and make sure that you're kind of doing things in the right order. So how am I going to write this? I'm basically going to use that notation that I introduced the other day, where if we wanted to, so the first thing we're doing in this is taking the derivative of the numerator, right? So what I'm going to write is I'm just going to write x minus 1 prime. And I'm going to use that as kind of a placeholder, where in the next step we'll go in and we'll actually write what that derivative is, but that kind of helps you set up so you know what you're doing. So we know that the first thing we have to do is take the derivative of the numerator. And then we know that we have to multiply that with the denominator, because that's the first part of the quotient rule. Okay, next part of the quotient rule is we subtract the derivative of the denominator. So we're going to do x plus 1 prime. And we're going to multiply that with the numerator. And in this case, the derivatives of x plus 1 and x minus 1 are very simple. So doing this whole prime business is probably not really going to make a difference, but I just wanted to start introducing it to you so that when we get to more complicated examples, you kind of know what it means. And so then we're going to divide by the denominator squared. So, okay, let's simplify, or let's actually write out these derivatives now. So what's the derivative of x minus 1? Well, it's just 1, right? Because the derivative of x is 1 and the derivative of negative 1 is 0. So we have 1 times x plus 1. And then what's the derivative of x plus 1? Well, it's the same, right? It's just 1 plus 0, so it's just 1. And then we're dividing this all by x plus 1 squared. And so now we can multiply, kind of combine stuff. We can get rid of those 1s. So we have x plus 1 minus x minus 1 divided by x plus 1 squared. And then if we combine like terms in the numerator, we're going to have an x minus another x. So that's going to become 0. Maybe I'll write that all out actually. So we have x plus 1 minus x plus 1 divided by x plus 1 squared. And so these x's, we are going to cancel each other out, and we'll be left with 2 over x plus 1 squared. And you could totally leave your answer like this. You could multiply out the x plus 1 squared. Again, I don't really care so much about whether things are factored or not in this context. Okay, so I want to look at a similar example now, which is it will look very similar, but there's a kind of a key difference to it. So let's say that instead of it being x minus 1 over x plus 1, let's say now it's x minus 1 over just x. So for this example, we actually do not need to use the quotient rule. So why don't we need to use the quotient rule? Well, because we can actually simplify this before taking the derivative. And we'll see that we would get the same answer. You could use a quotient rule and you would get the same answer, but it's going to be a lot faster to just split this up the way that we did like last week. So our first step in this case is we're going to rewrite it. So we're going to rewrite this as x over x minus 1 over x. And this simplifies to 1 minus x to the negative 1. So once we've rewritten it, now we can just use the power rule. Now we don't need to use any quotient rule. So the derivative is just going to be 0 minus negative 1 x to the negative 2. And that's going to be, the negatives cancel, so we're left with 1 over x squared. And if you want, go ahead and try to do this with the quotient rule, and you'll see that you'll get the same answer. It will just take a couple more steps to get there. All right, so we have 2 more examples we're going to do. So the next one is y is equal to x squared plus 5x minus 1 divided by e to the x. So remember that when you're taking the derivative of a function that is like in y equals notation, you can either call the derivative y prime or you can call it dy dx. Either one is fine. Okay, so we do have to use the quotient rule in this case because even if you were to split this up into 3 different fractions, you would still have to use the quotient rule on each of them. So you could do that if you wanted to, but that would actually make it harder, I think. So I'm going to use that same idea that I did in the other one and kind of write out, okay, we're taking the derivative of the top and we're multiplying that with the bottom. And then we're taking the derivative of the bottom and multiplying that with the top. Oops. I want to go back. Nothing's going how I want. Okay, there we go. And then that's all divided by e to the x squared. Okay, so now we can go in and take those derivatives. So what's the derivative of x squared plus 5x? It is 2x plus 5. And we still need to have parentheses, right? Because we're multiplying that whole derivative with e to the x. And then what's the derivative of e to the x? Well, that's just e to the x. And then we're multiplying that with x squared plus 5x minus 1. And then I'm going to rewrite this e to the x as e to the x times e to the x. So if you wanted to, you could distribute these e to the x's in, but I think that would actually just kind of make the next step harder. So I would actually just realize, and this is actually going to happen anytime you have e to the x as your denominator function. So anytime you have e to the x as your denominator function, it's just going to work out that you'll be able to cancel an e to the x from the denominator because that same e to the x is going to show up in 3 places. But let's factor it out like we did on the last step because I just think that's like a slightly better way of showing this. So if we factor out an e to the x in the numerator, we're left with 2x plus 5 minus x squared plus 5x minus 1. And we have to be sure to put parentheses because we still have this negative sign that needs to affect the second part. And then that's divided by e to the x times e to the x. And so now we can see that we have this extra e to the x that we don't need. We can get rid of that. And so we're left with 2x minus 5 minus x squared plus 5x minus 1 divided by e to the x. And now we can distribute this negative sign and combine some like terms. So we get minus x squared minus 5x plus 1 divided by e to the x. And then we want to put together things that have that are like combinable, right? So we have negative x squared, that there are no other x squareds, but then we have a, and I'm just looking at this because I think I made a mistake in my last video. So it's a good thing that I re-recorded this because I don't think I noticed my mistake the last time around. All right. Well, anyway, so we have x squared. Now we have a minus 5x and a plus 2x. So altogether, that's going to give us a minus 3x. And then we have a plus 1 divided by e to the x. So that is our final answer. All right, so I want to do one more example, and this last example, we're actually going to do it 2 different ways, and it's in order to kind of make a point. So our last example is we're going to find the derivative of f of x is equal to 2x squared minus 1 divided by square root of x 2 different ways. So the first way is we're going to use the quotient rule. And the second way is that we're going to simplify before taking the derivative. So before, remember, differentiate is our verb for taking the derivative. And in both cases, we're going to need to have our answer written in a simple way. So basically what we're going to see is that when we use the quotient rule, the first step is fine. You'll get to your derivative, but then when you go to simplify it, it's going to take a good amount of work to simplify it. Whereas if you simplify before you take the derivative, it's just going to make everything a lot easier. So I like to really emphasize this just because as much as I try to tell students that simplifying first is better, in my experience, you all tend to not do it. And, I just really want to drive home the idea that, and hopefully you'll see in this next example how much easier it's going to be if we simplify before we take the derivative. Okay, so let's say we are going to use the quotient rule. So that's our first method. So if we're using the quotient rule, we're going to start by taking, and actually, sorry, I have a typo here. This was supposed to be an x. Okay, so if we are using the quotient rule, we want to start by taking the derivative of the top. So I'm going to use my derivative notation here. So we're going to take the derivative of that, and we're going to multiply it with the square root of x. And then we're going to subtract from that the derivative of the square root of x times the numerator. So 2x squared minus x. And we're going to divide all of that by the square root of x squared. Okay, so what's the derivative of 2x squared minus x? Well, applying the power rule, we're going to get 4x minus 1. And then we're going to multiply that with square root of x, which let's rewrite that as x to the 1/2 because we're going to want to be able to multiply and combine things together. So let's rewrite it like that. And then what's the derivative of square root of x? Well, that's the same thing as x to the 1/2 as well. And we know that taking the derivative of x to the 1/2 is we bring down the 1/2 and we do 1/2 x to the negative 1/2. So I'm going to leave it written like that with the negative exponent because it'll just make it easier for us to combine it with the other things that we want to combine it with. Okay, and then square root of x squared, well, that's just x, right? You take the square root and then you square it, becomes just x. So if you were to write this as your answer on the test, technically it's correct, but I would not accept this as a full credit answer on a test because you haven't simplified it. There are things that, like, we'll see can really, really get broken down and combined, and we can make this way simpler looking. And one thing I just want to mention is that on the online homework, they will probably accept something like this. So the online homework, is a computer. If you type in two different expressions that are equivalent, for the most part, there are some exceptions. Some of the questions are coded so that only certain types of answers will work. But for the most part, you can type in something super complicated, and as long as it's technically correct, it will get marked correct. So I don't want you to think that just because you can type in a complicated, unsimplified answer on the online homework, that it will be acceptable on a test. So on a test, I want to see you simplify. So what would that mean in this case? And so I guess I would recommend that on the online homework, you simplify just for the practice of doing it, even if the computer will allow you to type in something that is not fully simplified. Okay, so let's go through this. So we have 4x times x to the 1/2. So altogether, that's going to give us 4x to the 3/2, right? Because x is the same as x to the 1, and you add the exponents when you multiply together. So 1 plus 1/2 gives us 3/2. And then we have minus x to the 1/2. And then the next part, we have negative 1/2. But that negative 1/2 is going to multiply with this 2 actually, so we can get rid of that, right? So right now we're multiplying together this and this. So that's going to give us just negative 1 times x, and then we have negative 1/2 times 2, and that's going to be 3/2, because 2 minus 1/2 is 1.5, which is 3/2. So now let's multiply together this and this. And I should have grabbed that negative sign over here too, because the negative signs are going to combine to become plus. So we have plus 1/2 x to the 1/2, right? Because this one is x to the 1, and then x to the 1 times x to the negative 1/2. 1 minus 1/2 is 1/2. So we're left with that. All divided by x. So this is still not fully simplified because we can combine like terms. We have some things that are the same, right? So we have a 4x to the 3/2, we have a negative x to the 3/2. So together that gives us 3x to the 3/2. So that's combining this and this. Then we have a negative x to the 1/2 and a 1/2 x to the 1/2. So together that's going to give us, so that's going to be negative 1/2 x to the 1/2 over x. Okay, so still not there. This is still not fully simplified because we can like break this down into separate fractions, and this x can get combined with stuff. So if we have 3x to the 3/2 over x minus 1/2 x to the 1/2 over x. So how does this work? Well, when you're dividing, you subtract your exponents, right? So we do 3/2 minus 1, and that leaves us with 3x to the 1/2. And then for the second one, we have minus 1/2. And what is the new exponent going to be? Well, it's going to be 1/2 minus 1, which is negative, oops, I forgot the x, which is negative 1/2. Oops. Let me just double check something. Yeah, okay, sorry. I got myself confused for a second. I hope this agrees with our answer. So we're about to do it a different way. And like I said, this is my second time going through this, so I'm starting to get a little delirious with this math. So I'm hoping that we get the same answer the other way. If not, we're going to have to retrace and see what mistake we made somewhere along the way. Okay, so let's see how much easier it is to do it the other way. So second method. So the second method is starting with our function And before we do anything else, rewriting it. So we're basically going to do the same type of simplification that we had to do in this step, but we're going to do it like only once, and then we're not going to have to do any of like all of this stuff up here. So if we rewrite this function, we would have 2x squared over x to the 1/2 minus x over x to the 1/2. So just splitting it up into two fractions and rewriting the square root as x to the 1/2. And so what's another way of writing that? Well, we can subtract our exponents, and this would be 2x to the 3/2, right? Because 2 minus 1/2 gives you 3/2. And then for this next part, we have x to the 1 over x to the 1/2. So that is going to be x to the 1/2. So if we've rewritten it and we have this as our new function, well, now we can just use the power rule. We don't need to bother with the quotient rule anymore. So how does the power rule work? We'll leave this 2 to the side. We'll bring down the 3/2, and then we'll subtract 1 from 3/2. So 3/2 minus 1 is going to give you 1/2. And then for the second one, we're going to bring down the 1/2, and then we have x to the negative 1/2 because we're subtracting 1 from 1/2. And if we simplify this, we end up with, if we multiply together, we get 3x to the 1/2 minus 1/2 x to the negative 1/2. And lo and behold, I hope, yes, it matches. It's the same. And look how much less work that was. So I'm going to put a question very similar to this on the final exam, and I'm curious to see. In past years, it's generally the case that students do it the first way for some reason. I don't know why, but maybe this will be the year that it's different and you all will realize that it's a lot easier if you do it the second way. All right, so like I said, the rest of the week we're going to be talking about the derivatives of trigonometric functions, and then that will give us an opportunity to start to really kind of play around with different combinations of functions and how we can add them, subtract them, multiply them, divide them, and take the derivatives of the resulting functions. So yeah, I'll see you in the next video.